Marchetti. I'm a professor of physics at the University of California in Santa Barbara, the United States. 3 years ago in June, as a matter of fact, I was contacted by email by David Hughes and Pat Diamond, who are two of the organizers, about this idea of organizing a 6-month-long program on what we now call anti-diffusion. And the thing about this program is that it's extremely broad. It actually brings together people working on from astrophysics and plasma physics to biological physics and what we call active matter. So at first it sounded very exciting, and I said yes immediately. Then it was a little bit, I realized how challenging it was. But overall, I think it sounds like it's gone very well, and it's been a great experience. And I guess the other organizers probably recommended me for the Kirk Fellowship. The title of my talk was Evading Newton's Law to Set Patterns in Motion. Clearly a title that requires possibly a bit of explanation. So Newton's law is the law that says that for every force there is an equal and opposite reaction. So if I push on somebody, that person exerts an equal and opposite force on me. It is the law that allows us to walk and swim. A more perhaps startling example is the launch of a rocket, where the gas expelled by the rocket is the action, and the push of the throws the rocket in the sky is the reaction. So these kind of interactions, we also call them reciprocal, but there are many examples in nature of forces that are non-reciprocal. First of all, in social settings, often things are non-reciprocal. And, but also in, say, for instance, the spreading of epidemics or the interaction between a prey and a predator. And often in biology, where there are protein cycles that control biological functions, such as cell division, where maybe one protein promotes its own growth, but another protein downregulates it or controls it or suppresses it. And so those interactions are non-reciprocal. And the point, so my talk was on understanding how these non-reciprocal interactions provide a mechanism for turning static patterns, such as, I don't know, the stripes you might see on a tropical fish, that's a pattern, to turn these static patterns, to turn them into traveling waves of oscillations. Because again, in the biological context, these proteins that interact with each other non-reciprocally often set up oscillations inside a cell, and this oscillation may promote cell division or traveling waves. And the relation to the anti-diffusion program is that one of the mechanisms that controls pattern formation is anti-diffusion, in the sense that most people are familiar with diffusion. You put ink in water, it diffuses until the concentration is uniform and water and ink are well mixed. But if you have oil and vinegar, they don't like to mix. And if you actually shake up to make a vinaigrette, therefore you mix them and then you let it sit, they will stay separate. That is, you'll have a layer of vinegar at the bottom and a layer of oil at the top. So that's anti-diffusion. And if you actually create non-reciprocal or chase and run interaction, as we call them, between the two concentrations of these two fluids, say, then one fluid diffuses and the other tries to catch up with it. And the result is that you get actually a traveling pattern of stripes, for instance. And so that was the topic of my talk, the mathematical formulation that describes this kind of phenomena. What I hope the audience took away from my talk is that the mathematical model we developed to describe this type of dynamical patterns is what we call generic, in the sense that it can be used for systems that are very different from, again, protein cycles and reactions in the cell interior, but also for synthetic materials that are actually particles that behave like engineered microswimmers, that have this type of non-reciprocal interactions and form these kind of patterns, but also maybe to describe, as I said, spreading of epidemics, so process on very different length and time scales. In general, my field of research right now is what we call active matter. And so what that means is a new type of materials made of entities that consume energy to generate their own motion. And these could be living things, such as birds. So you describe the flocking of birds and these giant bird flocks as a material. It could be living cells or bacteria that move together like a fluid. Or it could be synthetic microswimmer that actually organize in materials that can reconfigure themselves. And so the idea here is to use ideas and methods from condensed matter physics that understands how interaction between atoms and molecules lead to different types of materials to describe these non-equilibrium systems. And I think in these non-equilibrium systems, the anti-diffusion and pattern formation and dynamics occur all the time. And I hope my talk and the research I've done on this will advance that type of research and possibly ultimately lead to the ability to engineer new materials that maybe are self-healing or can actually mimic biology.